Here we have an integral from x to 2 pi sine t over t dt. And then we integrate from 0 to 2 pi dx. And then we want to prove this integral is equal to 0. First of all, I'm going to let this integrand equal to f. So f of x is equal to the integral from x to 2 pi. But I'm going to write it as minus of 2 pi to x. Let's interchange the boundaries and add a negative sign here of a sine t over t dt. And then let's find out the derivative. F dash of x is equal to minus of sine x over x. That's according to the fundamental theorem of calculus. Now, if we can rewrite this integral into integral from 0 to 2 pi of f of x dx. So we can just use u equal to f of x, then du is f dash of x, that is this, dx, minus sine x over x dx. Then what's dv? dv is 1 dx. So what is v? v is just simply x. Right, so we can use the integral by parts. Right, so now I is equal to uv x times f of x from 0 to 2 pi minus integral from 0 to 2 pi. Right, first of all, we have u dv, right, u dv, uv minus v du, v du, v times du, right, so minus xx sine x dx. Now, I is equal to, so first of all, we substitute x with 2 pi, right, 2 pi. And then here we have f of 2 pi. What's f of 2 pi? F of x, f of x, f of 2 pi. 2 pi to 2 pi integral becomes 0. Right, so 2 pi times 0, 0. Minus, we substitute x with 0. So 0 times f of 0, still 0. So this is this part, right, minus. Minus, minus, plus. X cancel out. So we have plus. Integral from 0 to 2 pi. Sine x dx. Now, the graph pi, 2 pi, graph of sine, something like that, right? So easily this area equal to this, the magnitude of this area equal to the magnitude of this area. They just happen to have the opposite signs, so therefore the area is equal to 0. So therefore this is automatically just 0, right? So in the end, I have 0. So indeed, the integral is equal to 0. So I'm done. Now I want to discuss the legitimacy of doing it like that. So the legitimacy of this step is because, first of all, we have this well-known theorem, which I've also proven in the previous video, that if a function g is continuous over this interval, then if we define this changing upper bound integral in terms of a function of f of x, then this derivative of f of x has to equal to g of x. X is restricted in this closed interval. Fundamental theorem of calculus. So therefore, first of all, g of t is in fact my sine of t over t. Right? It is indeed continuous over the interval delta 2 pi, as long as for any delta that's larger than 0, strictly larger than 0 and less than or equal to 2 pi. The reason is because delta cannot be 0, because t cannot be 0 in this case. Right? But this is already enough. This is already enough. This is also a closed interval. Therefore, according to this theorem, then we can easily prove that this result, right, the derivative of this changing upper bound function is indeed the inside function, the integrand just replacing t with x. Indeed, this is legitimate. But this is only when x is strictly larger than 0 and less than or equal to 2 pi. But this is fine, even though we don't include 0 in this case. But just a matter of difference of just 1 point does not affect the overall outcome of the integral. All right, so therefore now we must show that f of x, what property does f of x have? Right? I can claim that now f of x is indeed continuous over the interval excluding 0, over the interval open interval 0 to closed interval of 2 pi. Why? Because according to this theorem, so as long as I've also proven this theorem in a previous video as well. So I haven't proven this theorem yet, but I will prove this theorem perhaps in the future. But this one I've already proven. If the function g is a Riemann integrable over this interval, then its changing upper bound function can be proven to be continuous everywhere in this interval, AB. Right? So first of all, g of t can be easily proven to be Riemann integrable over this closed interval. Therefore, it's easy for us to show that, in fact, f of x changing upper bound. Right, so, changing upper bound, f of x is indeed continuous only over the interval delta to 2 pi. Right, here, delta is any positive number, strictly larger than 0. So this is indeed true. And don't worry about the 0, because it's only a matter of difference of just 1 point. So since it is continuous already, therefore we can easily show that it is indeed Riemann integrable over the interval delta 2 pi. Right? Any delta, any positive number. Right? This is indeed true. Therefore this is really meaningful. Even though we exclude the point 0, but this is still meaningful because it's only a matter of just difference of just 1.0. It doesn't matter. Does not affect the overall outcome of the integral. First of all, so nearby the point 0, so nearby point 0 is f of x bounded nearby 0. Right, so what's the... Right, so meaning when x is very close to 0. So here, when x is very close to 0, so any delta larger than 0, right? Integral from negative 2 pi to delta, it is indeed some Riemann integral. So indeed turns out to be some constant. Right? So indeed we can see that nearby 0, f of x is indeed bounded.